Hi, my name is Rehaan Kadhar, and I'm working on this project with Raymond to present the Davidson Fellowship Scholarship MQ Lung XILF, an expandable multimodal rate fusion system for improved clinical lung cancer diagnosis with automated medical reporting. So, before I go to my project, I want to explain two different topics. One being lung cancer. So, lung cancer essentially has two different subtypes, being non-small cell lung cancer and small cell lung cancer. In this project, we focus on non-small cell lung cancer because it accounts for about 85% of cases, with non-small cell lung cancer being differentiated into adenocarcinoma, squamous cell carcinoma, and large cell carcinoma, being its three different subtypes. And another topic I want to explain is explainable AI, which refers to artificial intelligence systems designed to provide clear, understandable explanations for their decisions, making AI models more transparent and interpretable for users. So, what this essentially means is that a whole AI model doesn't just give predictions, but as it gives its own prediction with high accuracy, it also explains why each and every prediction is happening throughout the whole model to give more like transparency or interpretability to the user. So, in our project, why are we focusing on lung cancer? What's its current state? So, lung cancer is responsible for about 23% of cancer deaths globally, causing nearly 235,000 new diagnoses annually in the US alone. Let that number just sink in, with about 85% linked to smoking. So, and in all honesty, smoking is not going to go away anytime soon in the next few years. It has about 5 years. It has a 5 year survival rate of just 20%, with survivors dropping to as low as 5% for advanced stages, and the majority of cases are diagnosed at a later stage when treatment options are limited. So what this means that as we increase the early stage diagnosis of these type of lung cancer cases, they can be more easily solved or like cured or like help the patients more better. So, despite the progress in deep learning models, clinical adaptation is hindered by a lack of transparency in AI decision making when combined with high accuracy predictions and a multi-model integration. With medical imaging, symptom analysis, and automated reports being critical yet complex tasks, integrating these modalities efficiently requires specialized techniques. This limitation is particularly relevant in lung cancer diagnosis, where explainability, data fusion, and model reliability must be carefully balanced with clinical trust and usability. So, to all these issues, what's our proposed solution? Our proposed solution is developing a multi-model late fusion AI system with three parallelly compiled unique tools integrated for each of CT scans, X-rays, and clinical symptoms, where we develop two learning powered networks. We developed two deep learning powered networks, improved with stacked ensemble modeling for both the medical imaging modalities, with the NLP models trained for the symptom modality, which is more textual inputs on self-generated clinical notes, pairing all of these models with explainable AI techniques for high interpretability. So the whole design process, we focus on robustness, where the model is trained on diverse medical imaging datasets and 10,000 self-generated clinical notes to ensure adaptability across various patient outcomes. We then focus on functionality, where we designed the whole model to learn relationships in multi-modal lung cancer diagnosis, to generate high accurate predictions along through a late fusion pipeline. We then focus on specification, where we integrate experimental AI techniques throughout the whole model to provide transparency in the decision-making process. So, what's the whole design framework? So, in this whole design framework, we first focus on pre-processing, where we standardize and enhance input data by normalizing pixel intensities, applying contrast adjustments, clash, and resizing medical images, while utilizing LLM model to generate 10,000 clinical notes. We then focus on the CD modality first, utilizing transfer learning with MobileNet V2, applying data augmentation, dropout, regularization, and stratified cross-validation to optimize multi-class lung cancer subtype classification. We then focus on X-ray modality, implementing a stacked ensemble modeling for fine-tuned CNNs, leveraging focal loss, mode balancing, and meta-learners to improve clinical classification robustness. We then focus on the symptom modality as the final modality we actually train a model for, training a span-based name entity recognition model on a self-generated clinical node dataset, extracting clear symptom features with fuzzy matching for structured diagnosis integration. We then work, after we finish developing all these three different independent models, we work on adding expandable AI techniques for each of these separate modalities, where we apply techniques like LAM, SHAP, GradCam, and PDP to provide both local and global model interpretation, ensuring clinical transparency in feature importance and decision-making pipelines. So after we develop all of these different set modalities, we apply a late fusion technique and then work on deployment, where we implement a dynamic weighted fusion strategy to aggregate modality-specific outputs based on confidence scores, generating automated medical reports, annotated visuals, and generative textual explanations. The whole flowchart can be seen on the right here.
For data preparation for the CT scan dataset, we first reduced the initial image collection from 1,967 images. For the X-ray dataset, we isolated two specific classes for binary classification. Both of these datasets then underwent extensive preprocessing pipeline unique to their respective datasets. For the symptom dataset, we leveraged a 6-bit quantized Mistral 7B.3 model generating 10,000 SOAP formatted clinical notes. Each note will contain 2 to 5 symptoms validated against our dictionary at 8% threshold. This leads us to our CT scan modality. Transfer learning was employed using pre-trained CNN models to perform multi-classification of 3 lung cancer subtypes listed below. With issues pertaining to class imbalance, we use weighted random sampling, class weight adjustments, and along with other techniques to address class imbalance. We explored six popular CNN architectures, and we utilized six metrics to evaluate all these six popular CNN architectures. As listed in the metrics below, MobileNet V2 performed the best and was chosen as the final CT scan modality. All CNNs were trained utilizing the 25 Apache per fold training dynamic to balance learning and overfitting prevention. For our next focus was on the X-ray modality, where a stacking ensemble approach was employed to address the significant class imbalance of 1 to 10 in the CXR14 dataset. It consists of two stages, as shown in our figure, where the first stage is the baseline CNNs, which is ResNet 18, Convex Tiny, EfficientNet V2S, and then DenseNet 121, trained on seeds of 615, 105, 522, and 422, respectively. For the second stage, these features were fed into classifiers, logistic regression, random forest, extra trees classifier, gradient boosting, ADA boosting, and light gradient boosting. Each were optimized independently for F1 macro score, and the final gradient boosting meta-learner would combine everything, utilizing SMOT to address class imbalance and plat scaling for probability calibration. For the final modality, for symptom modality, we utilized a span-BERT large model with continuous span masking and span boundary objective to recognize symptoms utilizing NER techniques. The system totally recognizes 22 unique symptoms across 8 symptom cluster rules and is able to successfully process natural language variations in clinical tests and find symptoms important for lung cancer. Finally, for a dynamic weighted late fusion model, we utilized a two-pronged approach where we first define baseline weights for all three modalities. We then aggregated these weights utilizing confidence scores as adjustments. This leads to a highly dynamic weighted late fusion that depends entirely on the modalities and their raw performance rather than just solely being baseline weights.
So once you worked on dosage modalities, worked on local expandable AI, with Lime being implemented for a C-scan and X-ray modality, with segments input images into superpixels, revealing which image areas most significantly influence classification decisions. We worked on GradCam, which provides valuable insights into which spatial features are more prioritized when detecting lung cancer indicators, which was done specifically for CT scan modality. Then specifically for X-ray modality, worked on meta-ensemble influence, with break down contribution of individual base learners within the stacking model. Then specifically for the symptom modality, worked on character indices, which enable precise visualization of where these symptoms appear in the text. After all this, we worked on global expandable AI, where SHARP was implemented for both X-ray and CT scan. For X-ray, it was implemented at two distinct levels, the meta-model feature attribution and meta-transportation analysis. For CT scan, SHARP was employed at a feature level to identify critical regions impacting subtype classification, highlighting the contribution of specific anatomical features to diagnosis. Next, we worked on PDP for the X-rays, where it visually represents the relationship between CNN outputs and meta-model decisions, demonstrating how meta-learners shape the meta-ensemble's final probability scores. Then PDP was done for CT scans, was done a bit differently. It was employed to captain speech ablation, which employing Gaussian node perturbation to assess classification confidence changes when specific image regions are removed. That with all these models and techniques finished, we worked on developing an automated medical reporting web application, where a final late fuse model is developed to a self-coded web app capable of providing inputs and receiving detailed generative medical reports. So as you can see in the image on the left on top shows the model shows us inputting images and writing our own symptoms, where the image below it shows the model being running. Afterwards, it results in the images on the left, which is a whole medical report as shown. The model analysis not shown actually on top is where the global XML AI images are shown. Next, so why is this whole project even important? Like, what's the whole outcome of this? The whole impact of this is the three C's: clinicians, cancer researchers, and clinical establishments, with the whole goal to help patients. By integrating multimodal medical data with advanced experimental AI techniques, this system provides a comprehensive framework for predicting, visualizing, and analyzing lung cancer diagnosis, ensuring both accuracy and interpretability to support clinical decision making and enhance patient outcomes. Our model had 99.60 AUC for CT scans, 97.66 AUC for X-rays, and 98.10% F1 scores for symptom recognition, showing how high our model's performance actually was. So overall, what's our next steps and conclusion? So for next steps, we want to incorporate additional medical reporting such as PET scans or MRI to further enhance the diagnosis accuracy and robustness of the model. Then we also want to develop adaptive weighing strategies to continuously optimize the late fusion process based on real-time confidence scores and evolving medical insights, improving both interpretability and predictive performance. As a conclusion, by advancing AI-driven lung cancer diagnosis, future healthcare systems will have improved early detection capabilities, leading to more accurate and accessible medical assessments. The same methodology can be applied to other medical fields, creating machine learning models that streamline diagnosis, optimize resources, and enhance overall patient care. Thank you.